So I've spent a large chunk of my career in probably about the last 5 to 10 years looking at how to get graph processing workloads flying on really large machines. And most of the reason I've done that is there are a lot of really important data sets and important applications that are best and most natively modeled using graphs. So it's really hard to underemphasize just how important graphs are, for example, to companies like Google and Facebook are, of course, but also things like our own national defense. Like these things play a very quiet, peaceful, but active role in protecting nations around the world. And so for that reason, they have a lot of value in processing them very quickly and performing things like anomaly detection and automated labeling have a lot of value for a lot of different industries. But in that role, looking at graph processing on big supercomputers, I kind of was watching all this deep learning stuff and it was kind of passing me by, right? Like there was a ton of work on CNNs and all variants under the sun, but they pretty much focused explicitly on regular data sets, like 2D pictures of cats or 3D volumes of seismic data or 4D or 5D volumes. All of these different techniques, the CNNs and the RNNs, they kind of made this implicit assumption that your data was regularly spaced and in a regular coordinate space so that you could apply these matrix operations, these dense matrix operations on these data sets. And so what that missed was all of this really high value, sparse, irregular, graph represented data sets. And so that's where graph convolutional networks come in. They kind of bring this deep learning blind spot into light and try to fix it using very similar techniques, but leveraging information about structural information in the data set itself, rather than just assuming that you've got a 2D or a 3D or a 4D grid where everything, all of the relationship information is encoded just in how you store the data rather than in the data itself. Now, I'm a graph processing guy, so I am not a statistician, and I'm still kind of exploring and learning this stuff, and so this is very much a organic work in progress talk. But I'm going to try to give everyone here the same impression of kind of what I've learned about graph convolutional networks, how they work, how they're useful, how you should think about them, what the intuition is behind them. And then I want to talk about how I've been exploring using them on a really cool streaming news data set called GDEL. Which basically is a streaming data set updated every 15 minutes of hundreds, or actually hundreds of thousands of news media outlets around the world in hundreds of languages, updated every 15 minutes. That tells you basically everything that's going on that you could care about. And then I'll kind of wrap out by talking about, this is one example of how you can use these GCNs. What are other things, particularly that might be relevant to kind of Houston companies? To really talk about graph convolutional networks, I want to start with what are convolutional networks, how do they work, how should we think about them, and then try to expand that to GCNs. So let's say you had some data set of images, and you wanted to train a model to pick out which of these images contain photos of Jan Odegaard and which do not. I don't know why you'd want to do this, but why not? Generally, the intuition behind convolutional networks is they use repeated convolutions across the image in order to hierarchically extract higher and higher level features with higher and higher level semantics. So maybe your first convolutional layer has a 3x3 filter with some number of channels output, and one of those channels is saying, is there a vertical line in my filter or is there not? And you give that a 0.8 probability. You apply another filter, and it goes, is that vertical line brown? And maybe it says it's 0.9. And then you add these semantically higher and higher level representations, and you fuse them, and you add jumps across layers and all sorts of things until at the very end, you collapse down to a single value or one hot vector that says this image contains Jan Odegaard or it doesn't. Now note, there are two important implicit assumptions about the data that you're working with in this kind of a network and in this kind of a design. So the first is that this information has locality embedded within it. So you don't need to say that the pixel at the center of this kernel is closely related to the pixel directly to its right, but less related to pixels that are 2 away or 3 away or 4 away when building up these hierarchical representations. You don't need to say that. That's just embedded in the information itself. And then so the second thing that we get is that nearness is defined purely by those image coordinates and nothing else. Now, the first is still true. Like, information has locality. When you're doing some kind of a graph processing algorithm, oftentimes the first thing you'll do is something like triangle counting or connected components to find what are things that are closely related by edges in the graph so that you can learn information about those, things like communities or connectivity or things like that. But the second just isn't true for graphs. The coordinates, the features, the attributes on vertices or edges in a graph have absolutely nothing to do with how they are related to each other. It's all about how these edges are connecting different vertices. And so what graph convolutional networks do is they strip away that assumption that your coordinate system matters, and they start to leverage the explicitly encoded relationships in your graph. So a brief recap on what a graph is. So a graph is just a collection of vertices and the edges that connect them. You can encode or think about or represent a graph as these 4 parameters. So you can have n, the number of vertices, d, the number of features per vertex. You can represent the vertices in your graph as an n by d matrix, and then you can represent the edges of your graph with an n by n adjacency matrix, assuming that you only have a single floating point value per edge. And so what this says is I have some number of points in space, these vertices. They're connected by some number of edges, and I can have an edge between any one of these vertices. In a really very simple graph convolutional network, a fully connected graph network, actually, you can represent that with this pretty simple equation, chain this together in multiple layers like you would like a regular deep neural network that's fully connected. So what this equation says is that in order to compute the output of a single layer, I'm going to apply a sigmoid or some activation, some nonlinear activation function to this equation, A times H of L times W of L. A is my adjacency matrix, which we defined over here to basically say where are all the edges in my graph. So we'll put a 1 anywhere there's an edge and a 0 otherwise. H of L is the output of my previous layer in my network. And so in the case of the first layer, which we're going to focus on today, that's X. That's just the features of my vertices. And then WL is some trainable, learnable set of weights, just like in any other neural network. So the cool thing that this does is it basically uses that adjacency matrix, that edge connectivity information, in order to extract out of X, your set of features, the features that you actually care about given the relationships in your graph. And so you can kind of think about this first term, the A times H, as using this row in A to strip out the values in this column of X, which is associated with a single feature we've got, in order to compute this little cell here. And so what this is basically saying is I want this cell to be some weighted sum of only the values, the features, this particular feature of any vertices that my vertex is directly connected with, essentially. And so that way, we're taking advantage of the relationship information in A in order to compute only on the information that we care about based on the relationships we have. And then you just do kind of the same thing you would in any kind of fully connected network. You apply your weights to that output. You apply some nonlinearity so that your model does something useful. And then you get some layer output, and you feed that onward to later layers. Now, there are 2 different ways to commonly use graph convolutional networks in the industry, though kind of still evolving. I think the talk from MD Anderson this morning mentioned this. This is a very recent topic and kind of just is evolving in 2018 and 2019 this year. But the most common kind of practical applications that you'll find in the research literature are either unsupervised or semi-supervised. Unsupervised is pretty cool because you don't need any labels, you don't need any information in your graph. You can just apply this and get some output. Unsupervised is generally used for anomaly detection. You can kind of think of it as a neighborhood relationship-aware hashing function, where you feed in your adjacency matrix, you feed in your vertex attributes, and you get back just some coordinate system collapsed. So you basically randomly initialize your network however you want. You can make it all ones, you can make it all zeros, you can make it some Gaussian function, whatever you like. You apply that to your adjacencies and your features, and you get out something, maybe a 2D coordinate system, maybe a 3D coordinate system, which maps your vertices to some point in that coordinate system. and then you can plot that. And you can visualize it, you can play with it. And the assumption is that because you're feeding both relationship information and feature information through this model, you're getting back something where things that are more similar, both in terms of their vertex attributes, the vertex attributes of their neighbors, of their neighbors' neighbors, of their neighbors' neighbors' neighbors, depending on how many layers you add in. You're getting back something where points that are close by in a 2D or 3D coordinate system that comes out of the hash function are also similar in terms of how they are related to their neighbors and what their neighbors' properties are. And so I'll show a quick example of this later. Semi-supervised is a little bit more intuitive and a little bit less wacky. You basically can have a partially labeled graph. So say you have a social network where you know some people are A&M grads, and you know some people are UT grads, and you want to hunt down the UT grads. What you can do is you can train a network on just the vertices that you have labels for and teach it what does UT grad look like with respect to other A&M grads and with respect to other UT grads. What kind of attributes does a UT grad have, and what does his social network look like, his or her social network look like. And then you can then reapply that network that you've just trained to the rest of the graph and just label everything else, for example. And so you might do this for something like, I don't know, terrorist networks if you were the DoD. So both of these are great classical examples of how to use GCNs on real-world data sets. GDELT, I mentioned earlier, is a really cool real-world data set that is live streaming every 15 minutes, containing breaking news articles from hundreds of thousands of media outlets, containing over 100 languages and going all the way back to 1979. It doesn't include the full content of each of these news articles, but it does come with information like the sentiment of this article based on natural language processing, the type of events that are referenced in the article, like country A negotiates with country B, or country A purchases land from country C, or person A kills person B, as well as unique identifiers for each of the actors that are associated with these events. And so with this, you can get a lot of semantic information, and you can also get URLs for these source articles so that you can actually pull them down and do your own parsing on these articles. And so what we did was we took a look at the GDELT data set. We took a look at modeling it as a graph and then applying GCNs in both an unsupervised and a semi-supervised manner to it. In particular, we focused on September 20th to 30th, 2019, so pretty recent. We filtered out any articles that the GDELT marked as low confidence, meaning that basically their NLP algorithms weren't working very well and they didn't have a whole lot of confidence in any of the semantic information that they were adding on top of them. We pulled down the web pages of all the source documents and removed any that we weren't able to wget because we're getting 404s or whatever, leaving us with about 226,000 articles. And then we built features out of that, things like the document tone, the type of events they were referencing, the actors that were referenced in those events, as well as one-hot encoded document titles in order to pull out some actual keywords and things. And so what you can do with this is, once you've built that data set, you can just randomly initialize a GCN and feed it through that network, and it'll give you something that looks like this. So this is a zero-centered plot in a 2D coordinate system. I would do 3D, but since I'm not on my laptop, I can't give a really slick demo. But I can do it in a 2D system, and you can do different types of anomaly detection. So in this case, what I've done is just a simple find the centroid and plot as anomalies anything that's some radius outside of the centroid. You can also look for things that are just the most distant from other vertices. The really nice thing is once you get into this 2 or 3D dense system, you can then apply all of your favorite regular machine learning algorithms. And if you've used the GCN to get there, which means you're respecting relationship information and features and attributes at the same time. You can also do wacky stuff with semi-supervised. So what we took a look at is could we automatically identify politically conservative or liberal documents using automated labeling. And so I put these in quotes because some people would say these articles aren't conservative or aren't liberal. We're just going to go with it and try not to cause too much controversy today. So given the assumption that we can classify most of the articles coming from Breitbart as relatively conservative articles and most of the articles from SFGate as relatively liberal articles, what we tried to do was train a GCN based on these relationships and then reapply that to the remainder of the graph to find other politically conservative or politically liberal articles. Our data set was about 416 SF Gate articles and about 55 from Breitbart, with around 69,000 total. At the end of the day, so first, should point out there's a pretty large class imbalance problem here, which we really didn't have time to account for very much. We had 400 to 55 conservatives, so that's pretty large class imbalance, and that reflected in kind of the labels that we got out of the data set. We got about 40,000 articles labeled as liberal and 4,500 labeled as conservative. If you use as a control something like CNN, which again, in my opinion, which you can disagree with, tends to be a little bit liberal slanted, and Fox News, which tends to be a little bit more conservative slanted, you do get some results that respect kind of that assumption. You get about 88% of them labeled as liberal for CNN, and only about 50 to 60% labeled liberal for Fox News. So again, higher for CNN, lower for Fox News, though probably not 100% accurate. And we did some kind of spot hand checking to take a look. Some of these labels make sense based on just kind of the keywords that you would get out of the titles. Of course, this is just one really simple example. You can do this with streaming sensor data off of large industrial systems. You can do this with social networks. You can do this with financial markets. Anywhere where there are already large graph representations or large graph data sets, GCNs have the potential to kind of revolutionize how you can do graph processing. And so with that, I'll kind of wrap up. I hope that this was interesting. I hope it was educational. And I hope you'll consider trying out graph convolutional networks and any graph processing workflows that you have today, or maybe just try out graphs and then GCNs. Thank you.
Thank you, Max. So while the next speaker sets up, maybe one super quick question for the speaker. Yes, let's do this one.
There's a question. Have you tried applying the same method to Euclidean data and see how well it performs, besides the speed penalty?
So you mean building a graph out of Euclidean data and then apply this?
To see how well it performs.
No, I have not. Do you have anything specific in mind?
Well, the correlations are implicit in the imaging data because of the structure.
So you're saying use GCNs on, so there are papers that show that they don't perform as well if you just build a 2D or 3D grid out of an image and then try to apply these. But it's hard to tell if that's because of a problem in the system or an immaturity in the field. Yeah, but there are papers that show that they don't perform as well.
Yeah, but there may be some other structural elements in the imaging data that you're missing, assuming adjacency, like vascular structures that are distributed in space, but could be correlated?
Yes.
Let's thank Max again.